Hello everyone, this is Pengcheng from Alibaba Cloud. I'm very glad to present SimAI. It is a high-precision, large-scale LLM training simulator. So why we need a high-precision LLM training simulator? We actually meet a series of practical challenges owing to diversities. First, model keeps evolving during time with different model architectures. These models are utilizing different training frameworks. Furthermore, GPUs we support are very diverse, including the NVIDIA Ampere, Hooper, Blackwell series, AMD MI series, and the India Gaudi series, and others. There are a lot of options in connecting these GPUs, including different choices of intra-host network, that is the scale-up network, and the inter-host network, that is the scale-out network. The most common use case for the simulator is that first we have a series of new scenarios to evaluate. For example, once a new type of GPU is introduced, we need to do a series of assessments to determine the best choice of the auxiliary equipments, including the number of NICs, the best corresponding network architectures. Second, there is a series of optimizations for various components used in the training. Fine-tune each mechanism for getting the best configuration also called for the high-precision simulation. However, delivering efficient and precise LLM training simulator is challenging. First, as mentioned before, the end-to-end model training system includes a SIG stack. To fully simulate the entire procedure requires a lot of efforts, while the precision cannot be well guaranteed. Furthermore, LLM training requires a large-scale GPU clusters. Additional challenges comes when we consider the scale. First, it is impractical to simulate large-scale GPUs programs on CPUs. Second, as shown in the figure, the classic network architecture is quite complex, making the entire simulation of large-scale, scale-up, and scale network slow. To solve this challenge, we propose SimAI. The overview of SimAI is shown in the figure. This project is completely open sourced. Welcome to try it directly. The first part is the workload generator, AICB. It generates the realistic workload for each simulation request. The output, called a workload description file, outlines the algorithm modules, collective communication operations, and their dependencies. Our workload generator hijacks existing training frameworks to produce workloads identical to real tasks. We keep the detailed workload executed on each host while masking all network communication. We have implemented this for Megatron and DeepSpeed, two of the most popular frameworks in our production scenario. Therefore, the LLM training can be executed on a single host without involving physical larger-scale cluster. The second part is the kernel simulation. In this part, we further decompose the submodules in the workload description file into multiple kernels. As a result, we transfer the precise simulation of computation kernels to practical single-host profiling. As a result, we transfer the precise simulation kernel to practical single-host simulation. The profile kernel executes results that stored in the database. For those scenarios where we cannot get the actual GPU profiling for profiling, we use the numbers on the GPU spec to deduce the execution time of all kernels, considering whether this kernel is computation-bound or memory-bound. The third part is the simulation for collective communication. This part, we transfer all collective communication operations to detailed point-to-point communication and conduct simulation based on our enhanced NS3. There are a lot of work we have been done in network simulators. However, these simulators does not aware collective communication, therefore cannot deliver precise simulation results. In SimAI, we propose SimCCL. It precisely transfers collective communication according to the NICO algorithms. This is the main workflow of SimCCL. In the initialization phase of SimCCL, we focus on generation the precise point-to-point communication strictly from Nichols' procedure. When simulation typically run on single host, SimCCL employs a similar hijacking technique to simulate the detailed peer-to-peer operations. We have done a series of modifications on Nichols: initialization, topology discovery, intra-host, and inter-host communication channel creation to finally complete this modification. After SimCCL initialized, the GPU kernel send operations are further masked and inserted and instead, we will generate a series of detailed NS3 flow model. To evaluate SimAI, we use 2 test beds, each with 128 GPUs, but the type of GPUs and the number of NICs on each host is different. For example, in the first cluster, we deployed the H100 GPU with each host with 8 H100 GPU and 8 NICs, while on the second cluster, each host containing 8 A100 GPUs with 4 NICs. The network architecture is Alibaba HPN. We compare SimAI with AstraSim. First, we evaluate the accuracy of communication. The inter-host communication comparison, SimAI is significantly outperform AstraSim, especially simulating small-sized messages. In the intra-host evaluation, SimAI can keep the error below 4%. On the other side, AstraSim has the 51.7% to 74.8% errors. We further demonstrate the computation simulation results. In 3 different types of GPUs, the A100, H100, and H20, SimAI can generate accurate communication cost for various kernels compared with the ground truth. However, AstraSim always generates kernel execution time with higher values, leading to poor simulation accuracy. Here we present the end-to-end model training simulation performance. We use GPT-3 13 billion, GPT-3 175 billion, and the Llama 65 billion as representative models. SimAI can precisely simulate the execution time compared with the ground truth, which is 36 times better than AstraSim. I will further show 2 cases we utilize SimAI for benefiting our production. The first is finding the best combination of parallelism strategy for our new proposed MOE model, without consuming large amount of GPU hours to try every combinations of the parallelism strategies. SimAI can directly propose the best setting for the expert parallelism, and it has been validated through the actual deployment. The second is using SimAI for guiding us designing better network architecture. From the simulation, with the scale-up network size continuous growth, the performance becomes better, verifying that building larger scale-up network in the future is very meaningful. And it also guides us to put forward this effort to extend the scale-up network. Last page is our future work on SimAI. Nowadays, SimAI is mostly focused on precise simulation of the training phase, while with the inference becomes much more popular. We will further extending our work to support the simulation of inference scenarios. We also plan to support the multitask simulation in the future versions, since that when we're considering a very large scale of clusters, the occurrence of multiple tasks is a trend. And finally, thanks for the listening, and don't hesitate to try our open source project. Thank you.